Hi, this is Mrs. Roble. This is part 2 of ionic compounds and metals. So we, in the previous video, had talked about ions and how to name them and how to write formulas. Now we're going to talk about the properties of ionic compounds. Now, because of the bonding that occurs with ionic compounds, they are typically solids at room temperature. So you're going to notice a lot of the ionic compounds are like salt. They're essentially solids. Because of the bonding that takes place within ionic compounds, they have extremely high melting points. They also have very high boiling points, and that illustrates their stability. So ionic compounds typically are very strong when we look at the bonding. We'll eventually compare them to covalent bonds, and you're going to find that ionic compounds are hard to separate chemically versus covalent bonds. Now, as I mentioned in the previous video, ionic compounds tend to form electrolytes in water. And because they form electrolytes, they're very good at conducting electricity, and I should have shown you by now a demonstration illustrating why they conduct electricity. Okay, because the ionic compounds form solids, they are very hard and brittle. We're going to talk about metals and their bonding and why they have the properties that they have. As I mentioned before, the ionic compounds are soluble in water, and when they dissolve in that water, they actually undergo what we call dissociation, so they separate out into ions. So for salt, it would be sodium and chlorine. So this diagram here shows you what happens to solid ionic compounds. So if we were to apply a stress to them like a hammer, notice what happens is the ions shift, so the layers, they sort of misalign with each other, and when you have two like charges together, they actually repel each other. So this makes it easy for the ionic compound to actually separate and break apart. Okay, so this is an example of dissociation, and what happens is we have a universal solvent, which is water, and it's this small molecule here, and what it essentially does is it goes over to an ion within the solid. So this block is essentially a solid ionic compound, and when it completely surrounds an ion, it turns it into a liquid. So notice that water completely surrounds sodium ions. It also completely surrounds chlorine ions. So until that ion is completely surrounded by water, it won't technically be dissolved. At the bottom here is a dissociation equation. So we have sodium chloride, and notice that it separates out into sodium 1 plus and chlorine 1 plus. Okay, so now what we're going to do is we're going to take the information that we gained about the different ions and their formulas, and we're going to look at what we call Lewis structures. So Lewis structures, we're actually looking at the outer electrons. So here we have sodium, and it has one outer electron. Now because it's a metal, it's very good at giving up its electrons, and notice that it's going to donate its electron to the nonmetal, and notice there's one little space for the electron that sodium is donating. The goal for most nonmetals is to have 8 electrons. So please notice that the nonmetals, when they form the anion, they want to have 8 electrons around them, and we use this notation to determine how many electrons does the nonmetal have. Notice that after sodium donates its electron, it gets a positive charge. So it has no more outer electrons, and it assumes a noble gas that is in the row above it. So in other words, sodium becomes like the noble gas that's listed in the row above it. And then chlorine has 8 electrons. Because it has that additional electron, it has a negative charge associated with it. Okay, here's an example of magnesium, and it's bonding to chlorine. And in order for that to happen, we need 2 electrons from magnesium. But the interesting thing is, only 1 electron can go to chlorine. So because of that, we need to have 2 chlorines. And this is why I was drawing the equations that I was the other video. So here we have magnesium, which has 2 electrons, and notice only 1 of the electrons can go to chlorine. So we actually need 2 chlorine atoms for every magnesium atom. And this is how we essentially draw the Lewis or dot diagrams for the ions that are undergoing ionic bonding. So you're going to get very good at doing this, and I'll show you some examples and you'll practice on your own. Okay, so here we have aluminum oxide, and the interesting thing is that aluminum has actually 3 electrons and oxygen only needs 2. So in order to balance the charges, this is all about creating a neutral ionic compound. So notice that there's 3 electrons within 1 aluminum, and the interesting thing is, okay, 1 oxygen can take 2 of them, but that 3rd electron has to go to a 2nd oxygen atom. And then the 2nd aluminum will donate 1 electron to that 2nd oxygen atom, but then it has 2 left, and it can give it to a 3rd oxygen atom. So when we draw the dot diagrams, notice that we have 2 aluminums, and they have a 3+ charge each because they each lost 3 electrons. And remember, with nonmetals, the goal is to have 8 electrons. And notice that each oxygen has 8 electrons because it essentially gained 2 electrons from an aluminum atom. Okay, so we're going to practice dot diagrams, and I have essentially 4 problems. I'm going to do the first 2, and then you're going to do the next 2. Okay, so what I would do with this is, first I would look at what ion are we forming, and then once I figure out the ions, I want to balance the charges. I want to make sure that the metal is donating the right amount of electrons for each nonmetal. Okay, and then I'll show you the dot diagrams for each. Okay, so what I want to do is I want to look up cesium phosphide, and phosphide is essentially phosphorus with a negative ion. And let's see what charges do we have here. So I have my handy dandy periodic table, and I put the charges on the top here. I highly recommend that you do that for when you're studying. So notice that the first 2 columns we have a 1+ and a 2+, and then this column over here we have a 3+. I'm omitting this column because it's kind of a nebulous column. There could be positive charges, there could not be. Here I have 3-, 2-, and 1-. Now let's look up where is cesium. Okay, cesium is in this first column, so I have a 1+ charge. And if we go over to phosphorus, phosphorus is a 3- charge. So this is what I would do. Okay, so we're going to do cesium phosphide. Okay, so what I would do is I would write out 1 cesium molecule, or I'm sorry, 1 cesium atom, and I'm going to put 1 dot there, and then phosphorus. Now, phosphorus has a 3-, and when I'm looking at the number of atoms, I have 1, 2, 3, 4, 5 phosphorus electrons. So the problem is there's 3 locations that I can add an electron. So if you had to guess, how many more cesium am I going to need? Hopefully you said 2. Okay, so I'm going to put another cesium over here, and another electron, and then a third cesium with another electron. And then I'm essentially just going to draw where I'm putting the electrons. And then I'm going to draw an arrow to symbolize the reaction. So I'm just going to line up. I have 3 cesium ions. And notice they all have a 1 plus charge. That 1 is understood. And then I'm going to have 1 phosphorus ion. And notice that I have a total of 8 electrons around phosphorus. And that has a 3 minus charge. So that's the dot diagram for cesium phosphide. Now let's go back to the next one. The next one is magnesium iodide. Okay, so if you go to your periodic table, and hopefully you see on the periodic table magnesium, or Mg, is located in the second column. So it has 2 valence electrons, 2 outer electrons, and then the question is iodine. How many electrons does iodine have? Notice it's in the 1 minus charge column, so it needs 1 more. Therefore, it has 7 valence electrons. So I'm just going to put the valence electrons around iodine. And I have this method where I put 1 on each side of the letter, and then I leave it blank where I have a missing gap. Now notice there's 2 valence electrons here, and there's 7. Iodine only needs 1 more. So how many more iodine ions am I going to have? Correct, I need 1 more. Okay, so I'm going to put it below here. Okay, so I'm just going to draw my arrows where the electrons are going. Okay, and then draw my arrow for my reaction. So my cation is going to be Mg, and it's going to be a 2 plus because it lost 2 electrons. And then I'm going to have 1 iodine, essentially has all 8 electrons. And then its overall charge is going to be negative. But I'm not done. I have a second iodine that I'm going to draw. Okay, so here I have 1 magnesium iodine. I'm sorry, 1 magnesium ion and 2 iodide ions. So don't forget, you're going to do lead sulfide and indium oxide on your own. And don't be surprised if you see them in the video assessment.